Voltage tends to drop off along a distribution feeder. It can also fluctuate above and below acceptable levels due to changing load conditions on the system. In order to maintain service to customers in a useful range, it's often necessary to install voltage regulators on the system. Voltage regulators are a type of variable ratio voltage transformer. They're designed to automatically respond to a voltage that is above or below a predetermined level by changing the relationship between the transformer windings inside the regulator. This adjusts the voltage on the load side of the regulator so that it remains within acceptable limits. Of course, voltage regulators vary as to their specific design, depending on the manufacturer, and the specific requirements of the system on which they're installed. As you watch the rest of the program, be sure to make note of any differences between the regulators you see here and those used on your system. If you have any questions, ask your instructor. Let's begin by looking at two basic types of pole-mounted voltage regulators that are used in the industry today. They are induction regulators and step regulators. Either is capable of raising or lowering the voltage. 10% is generally the maximum amount of voltage that is raised or lowered. Induction regulators are able to adjust the voltage in a continuous fashion, while a step voltage regulator has a number of taps and responds to a changing voltage by moving from one tap to another in specific steps. Let's take a closer look at each type. This is a simplified illustration of an induction voltage regulator. Here we can see the distribution feeder with a break in the line, so that there is a line side and a load side of the feeder. The primary or moving winding is connected to the line side of the feeder at one end and to a ground on the other end. The secondary or stationary winding is connected in series with the feeder. During normal operation, there is a voltage on both the primary and secondary windings. The voltage is indicated by yellow arrows. Additionally, the current on the primary winding forms a magnetic field which can cut across and magnetically couple with the secondary winding. This induces a voltage moving in the opposite direction of the voltage in the primary winding. The induced voltage is shown by a red arrow. When the direction of the voltage induced in the secondary winding is opposite to the existing voltage in the secondary winding, the existing voltage is bucked or decreased. For example, here the two windings are lined up so that the magnetic coupling between the two windings induces the maximum voltage in the secondary winding. Since the induced voltage is in the opposite direction to the voltage already in the secondary winding, the voltage on the load side of the regulator is reduced by a full 10%. So if the line voltage is 2400 volts, the primary winding in the full buck position would cause the voltage on the secondary winding to decrease by a full 10%, or 240 volts. The voltage on the load side of the regulator would be 2160 volts. If the primary winding is rotated to a 45-degree position in relation to the secondary winding, the effective coupling is reduced to 5%, or 120 volts. The load side voltage would be 2280 volts. When the primary winding is moved to a position that is 90 degrees in relation to the secondary winding, there is no magnetic coupling between the two windings. The voltage is the same on both the line side and the load side. This position is usually referred to as the neutral position. As the primary winding continues to rotate, the direction of the induced voltage on the secondary winding changes. This causes the induced voltage to boost or raise the voltage on the secondary winding. When the primary winding is at its full boost position, the voltage on the load side of the regulator will be increased by a full 10%. In this case, the voltage is increased by 240 volts, to 2640 volts. Remember, because the movement of the primary winding in an induction voltage regulator is continuous, the change in the voltage is also continuous. The other type of voltage regulator we talked about was a step regulator. Like the induction regulators, the step regulator has two windings. Here the windings are called the shunt winding and the series winding. Neither of the windings moves in a step regulator. The shunt winding is connected on one end to the load side of the phase, and on the other end to a ground. The feeder is interrupted at the regulator so that there is a line and load side of the feeder. The series winding is connected in series between the two sides of the feeder. In this step voltage regulator, 8 taps are connected at different places on the series winding. Each tap ends in a contact. A 9th contact, not connected to the series winding, provides a neutral position for the regulator. A bridging reactor is used to connect the taps to the line side of the feeder. The reactor can be moved from tap to tap, changing the number of turns on the series winding that are part of the circuit. For clarity, we will show the whole bridging reactor moving. In reality, only the contact arms at the end of the reactor move. The bridging reactor prevents the circuit from breaking between taps by maintaining contact with at least one tap at all times. When it makes contact with 2 adjacent taps, it provides an intermediate position and compensates for the difference in voltage between the 2 taps. In this way, it increases the number of steps between neutral and full buck or boost from 8 to 16. In this regulator, the maximum increase or decrease in the voltage is 10%. Each of the 16 steps above and below the neutral position represent a change in the voltage of 5/8 of 1%. On a 2400 volt primary line, each step would change the voltage approximately 15 volts. The ends of the series winding are connected through a reversing switch to the shunt winding on the load side. The reversing switch allows the direction of the voltage to be changed in the series winding so that the same 8 taps can be used for both increasing and decreasing the voltage on the shunt winding. When the switch is in the position labeled R, the voltage is raised. When the switch is in the L position, the voltage is lowered. Let's take a look at a couple of examples of how the step voltage regulator works. In each case, the current flow through the circuit is shown with a lighter color. If the line voltage on this circuit is 2400 volts and the bridging reactor is in the neutral position, then the voltage is 2400 volts on the load side. If the reversing switch is in the raised position and we move contacts of the bridging reactor to between the neutral position and the first contact for step 1, then the voltage is raised by 5/8 of 1%, or 15 volts, to 2415. Moving the contact arms fully to the first contact is step 2 and would increase the line voltage by 1.25% to 2430. This would continue until the bridging reactor was fully on the last contact. This is the full boost position, and the voltage is changed by 10% to 2640. Let's go back to the neutral position and change the reversing switch to the lower position. This would cause the load side voltage to be lowered in 16 steps of 5/8 of 1% each until the minimum voltage of 2160 was achieved. Both induction regulators and step regulators use a control circuit to sense voltage fluctuations on the load side of the regulator and keep the voltage within preset limits. While there are several kinds of electromechanical and solid-state control units available, the principles of their operation are similar. Let's look at a drawing of a simple electromechanical control circuit so we can see how it works. Once again, the current flow in the circuit is shown with a lighter color. This control circuit is powered through a step-down transformer connected at the load side of the regulator so that the voltage on the circuit is in the secondary range. The circuit has a motor which is connected through two motor control relays. The motor is used to move the windings or change the taps, depending on the type of regulator used. One relay operates the motor in the direction that raises the primary voltage. The other relay operates the motor in the other direction to lower the primary voltage. A beam positioned on a pivot between two contacts has a voltage in the 120 volt range. This voltage is used to operate the motor control relays. A solenoid moves the beam. Its movement is balanced by a spring pulling the beam away from the solenoid. The secondary voltage energizing the solenoid is always proportional to the primary voltage on the load side of the regulator. In a 2400 volt system, this proportion is 20:1. So we can see that the control circuit responds to changes in the secondary voltage. This control circuit has been adjusted to a range from 120.5 to 123.5 volts, or a total range of 3 volts. As long as the voltage on the control circuit remains between 120.5 volts and 123.5 volts, the control circuit will not cause the regulator to adjust the primary voltage. This range is usually referred to as the bandwidth. The bandwidth prevents the mechanism of the regulator from having to respond to minor voltage fluctuations and prevents excess wear and tear on the voltage regulator. The control circuit can be set so that the beam is zeroed between the two contacts at a specific voltage, in this case 122 volts. If the load voltage increases so that the step-down voltage on the solenoid is above 122 volts, the beam moves toward the lower contact. At 123.5 volts, the beam makes contact with the lower lead, and the motor adjusts the windings of the regulator so that the load voltage is decreased. This causes the solenoid to move the beam back to a position between the two leads. If the load voltage had lowered, making the step-down voltage less than 122 volts, the beam begins to move toward the upper contact. Once the beam contacts the upper contact, in this case at 120.5 volts, it would cause the motor to adjust the windings of the regulator by increasing the load side voltage. This, in turn, moves the beam back to its center position. In this part of the program, we looked briefly at how induction and step voltage regulators work. When we come back, we'll take a look at how a step voltage regulator is installed on an overhead feeder, and we'll watch as a crewman troubleshoots a voltage regulator.